And it is almost a continuation from what we did before. That is the root locus. And the Routh stability method usually uses two steps. We are going to look at the two steps that we are supposed to use. First of all, you can always determine whether system is stable or not by looking at the polynomial equation that you will be given. For example, if you are given a polynomial equation like s raised to power 4 plus 3s cubed plus, let's say, 2s plus 3, let's consider these polynomial equations in order to make a conclusion, A. Then B, we have s raised to power 3 plus 2s squared plus 3s plus 1. Then we talk about C, which is s raised to power 5 minus 4s raised to power 4 plus 3s raised to power 3 plus 2s squared plus 5s plus 2. So consider these ones as the characteristic equations of the polynomial. Then from there, we can take another one, s raised to power 5 plus s raised to power 4 plus 5s cubed plus 2s squared plus 3s plus 2. And finally, we can talk about E, which is s raised to power 5 plus 2s cubed plus 3s squared plus 4s plus 5. So we can look at those particular equations. And as I've said, this stability method, you only take the characteristic equation. Sawa sawa. So consider these ones as characteristic equations, which are now the denominator. Whenever you are using Routh stability method, always you use the denominator. Are we together? So for a system to be stable under this, then one thing that must be there for the first step, we are going to look at all the coefficients must be present and positive. Sawa sawa. All the coefficients must be present and positive, which means if the highest coefficient is s raised to power 4, then we must have a coefficient for s raised to power 3. We must have a coefficient of s raised to power 2. We must have a coefficient of s raised to power 1. And we must have a coefficient of s raised to power 0. So if all the coefficients are present and positive, then the system is likely to be stable. Sawa sawa. We are saying that it is likely to be stable because we are talking about the first step. Sawa sawa. So you can consider that it is stable, and then you can now move to the second step in order to see if you can confirm whether that particular system is stable. That is now the second part, which is now by the use of the Routh array. If all the coefficients are positive, but there is one that is missing, then the system is said to be critically stable. Sawa sawa. All of them are there, like this is now raised to power 4. Maybe we can say, like in this case, the one that is raised to power 2 is missing. Sawa sawa. Are we together? Yes. The one that is raised to power 2 is missing. Therefore, we can say that this system is critically stable. If there is a negative in any of the coefficients, then the system is unstable. So that is how you determine stability by Routh. And we've said that that is the first step. After that, then you can go further and investigate the roots by use of the Routh array, which we are going to look at maybe after some time. Are we together? So I want us to look at this and then check on their stability. Then we can say which one is stable, which one is unstable, and which one is critically stable. From what I've given, I'm repeating that if all the coefficients, the system is stable. If one of the coefficients is missing, then the system is critically stable. And when one of them is negative, any of the coefficients is negative, then the system is unstable. So that is what is going to determine stability. So from that, the first one is reason. Which one? So here we have critically stable. Sindio? The second one? The second one? Stable. The third one? Unstable. The fourth one? Stable. And the fifth one? Critically stable. Yes? That is a negative. No, that is why we are saying that it is unstable. As long as one of the coefficients is negative, then it is unstable. Sawa sawa. So that is how you are going to look at this particular system. So you'll find that one of the things that we can say is that whenever you are looking at this, please ensure that you take the characteristic equation, then put it write it in this way. Yeah? Write it in form of polynomial. Then from there you will be able to know whether the system is stable or not. So this is just the first part. It does not mean that if this one is stable, then it means that at the end of the day you are going to find it to be stable. Sawa sawa. You are still going to take it through the second process where you are going to make the Routh array. You are going to make the Routh array, and from the Routh array you are going to use that in order to find whether the system is stable or not. So you will find that when you talk about this, well, let's consider a polynomial equation like this so that we can look at the Routh array. So let the characteristic equation be an Sn plus an minus 1 Sn minus 1 plus an minus 2 Sn minus 2, and this one should continue until you get to a1s plus a0 s0. So consider that one as the characteristic equation. So if we consider this one as the characteristic equation, then you'll find that we can talk of the a terms as now the coefficients. Sawa sawa. Then it means that all the a terms for this system to be stable, then all the a terms which are actually the coefficients must all be positive. All of them must be positive for us to say that the system is stable. If any of them is negative, then we can say that the system is unstable. So this one is what we are going to use in order to find that. So let's look at how we are going to make the equation. So we can draw that. So this is how the Routh array is going to be done. So we start with the highest power, s raised to power n. Sawa sawa. S raised to power n. Then we go maybe s raised to power n minus 1. We can go to s raised to power n minus 2, s raised to power n minus 3, s raised to power n minus 4, and we can go through that until we go to s raised to power 0. So we don't know what is there until we can go to s raised to power 0. Then how do we fill this? You are only supposed to fill the two rows. Are we together? You are only supposed to fill in every aspect. You are supposed to fill only the first two rows. The rest you are supposed to calculate. To fill the first row, for the s raised to power n, we are going to have a n. Are we together? We take the coefficient a n, then we jump this, yeah, and go to n minus 2. So we are going to have a n minus 2. Then we jump the next. If we jump the next, we are going to jump which one? N minus 3. Then we go to a n minus 4. Is that okay? So take this. And then you can see now we have the next one is the coefficient for s n minus 1. So we come here there and write a n minus 1. We jump minus 2. We go to a n minus 3. We jump the next. We go to a n minus 5. you are only supposed to fill the first 2 rows. Don't fill everything. Of course, at one particular point, you will find that this one will just be A0. But that one, you will prove it later. It will be A0. If you do your calculation, it will be A0. So all this, you are supposed now to go ahead and calculate. So we can go ahead and calculate. So we can call this one B1. We can call this one B2. We can call this one B3. C1, C2, C3. D1, D2, D3, and maybe E1, E2, E3. So those ones are now what we are supposed to calculate and find their values. So whenever you want to get this, then you can remind yourself of the matrix. And from the Routh array, what we are going to consider so that we say that the system is stable is by looking at the first column. Therefore, at every time when you will be dividing, you must be divided by a value from the first column. No? Because it is the first column that is always used to know whether the system is stable or not. If all the values, or rather all the roots in the first column are positive, then the system will be stable. If any of them is negative, then the next thing that will be asked is how many roots are found on the right-hand side of the S-plane. You remember the S-plane? When we were talking about poles and zeros, we say that as long as there is a root on the right-hand side of the S-plane, then it means that that particular system can never be stable. It means that that particular system can never be stable. And therefore, we can simply be asked how many roots that are found on the right-hand side of the S-plane, but not whether the system is stable or not. Is that clear? So, we are going to do our calculation. We'll start by looking for the B1. So, if you want to get B1, so the B1 here, you can say B1 will be given. So, this one, you are going to use almost the same method that you use in order to get the determinant, but almost opposite. Yeah? So, we are going to get this an minus 2. Are we together? Times this. Matrix najua mnafanya hivi to get the determinant. You do this minus that. But here we are going to do this minus this over this. Is that okay? Yeah? So we are going to have, in that case, we are going to have an minus 1 times an minus 2 minus an times an minus 3 over an minus 1. An, so this times that. An minus 1 times an dot an minus 3 all over an minus 1. Yeah? No, we are supposed to subtract in between. No, we are supposed to subtract in between here. These ones we multiply, that's we then subtract that. Another person can still do it this way. This minus this over that times this. We'll try to expand that and you see what comes. An, we are simply saying an minus 2 minus an all over an minus 1 times an minus 3. If you expand it, that one will come there. Is that true? Is that true? We're going to have an minus 2 dot an minus 1 times, no, minus an times an minus 3 all over an minus 1. Is it the same? Yeah? So you can use the one that you find easier for you. You can talk of this minus this over that times that, or this times this minus this times this over this. So that is how you are supposed to get that. Is it clear? So I want us to look at how are you going to get B2. B2. As we have said, the first column must always be involved. So you must ensure that you use the first column. So for us to get B2, B2 is going to be given by, we are going to ensure that we seal this so that it is not there. So we use the 4. We use the 4, that, applying the same way. So it's going to be this times this minus this times that all over times that. So there are two methods. You choose the one that is easier for you. Are we together? Yeah, you choose the one that is easier for you. So we are saying this minus this over that times that, which is simply B2 is going to be, what is B2 now going to be? AN minus 4 times, yeah? AN minus 1 minus AN minus 5 times AN divided by AN minus 1. So that is how you are going to get that, so that you get all those particular values. It will be simpler, especially when we have the real coefficients like this. It will be simpler because instead of writing all these particular letters and the rest, you will be writing now the numbers. These ones are going to be numbers. So we are going to calculate by using those particular numbers. And you are supposed to do that. I want you to get, I don't want to get B3 because there is nothing the other side. So we can get C1, C2, D1, D2, E1, E2. Can we do that? The expressions for that from that particular array, so that we are able to know how to get all those particular values. Then after that, we can now go ahead and look at a real example. We can start with C1. C1. Yeah? C1 is here. So we are saying B1 times. So we are going to use this. So in that case, we are going to use this 4. Yeah? Are we together? Is that true? So it's going to be this times that. So we are being told that it is B1 times AN minus B2 AN minus 1 all over B1. All over B1. Then what of C2? C2? B1 AN minus 5 minus B3 dot AN minus 1 all over B1. Is that okay? You can go ahead and get D1, D2, D1. So what do we say? I'm waiting for D1, D1, D1. C1, B2, minus D1, C2, B1, B1 C2 all over C1, E1, no, D2, C1, B3, B1, C3 all over C1. Then we can get E1, and then from there we can see if we can do an example. I hope everyone is getting what we are doing. Huh? Nobody is lagging at a certain power factor. E1, C2 D1 minus C1 D2 all over D1. And you can go ahead and do everything for all that. So after you have completed all this, the arrays, then you are now, after completing all those arrays, then from there you are going to look at the first column. Sawa sawa. And if all the coefficients in the first column are positive, then the system is stable. Are we together? So after you've done all the calculations for all the elements in the Routh array, then you now come to the first column. You are only going to look at what is there in the first column. Should all of them be positive, then we can say that the system is stable. So now the use of the Routh array is now the second step in order to confirm whether from the coefficients that we looked at or the coefficients of the characteristic equations that we looked at, if they were all positive but maybe there was a certain negative somewhere, it will be confirmed by the use of the Routh array. Yes?
How did you say about the third column?
The third column? Just leave it. You will not. Yeah, there is no need to calculate. In most cases, what will happen is that when you have this third column, it means that that one will be the lowest coefficient, which means there is nothing the other side. So there is no need to calculate. You will be able to see when you can get it and when you cannot get it from the real polynomial equation when given. Yes. So I want us to look at an example. Are we all here? Can say example. So you are supposed to determine if the following characteristic equation, so this is a characteristic equation, you are supposed to determine whether that particular characteristic equation is stable. You are supposed to determine whether that characteristics equation represent a stable system. Are we together? So in that case, you are supposed, looking at it from the first stage, you can see that it is stable. So you can go and investigate further by use of the Routh array. Is that okay? So we can have it that way, so that the highest power is s raised to power 3. Are we together? And it will be followed by s squared, followed by s raised to power 1 and s raised to power 0. Then we fill it. What is the coefficient of s raised to power 3? 1. We jump that. What is the coefficient of S? Raised to power 1, 8, and then there is nothing here. The other side. Is that okay? We go to the second one. The coefficient for S raised to power 2, 4. We jump that one, then we come to 12. Remember, we said that you are only supposed to fill the first 2 rows. The rest you are supposed to calculate. And whenever you are calculating, don't calculate from the calculator without showing you are working. That is a mistake that people usually do. Just come, unakuja tu unaandika tu answer. And then somebody asks them, you make the person to ask himself, where did this answer come from? Yeah? You are supposed to show you are working. Either you can do it the other side, or you can do it, you can make this spacious enough. Right? You can make this Routh array spacious enough so that you do your calculation inside. Or you can just do the calculation the other side, like that. You can call that one even B1, B2, maybe D1, right? Then you say for B1 is equals to, it's going to be, 8 times 4 minus 1 times 12 over, all over 4. And what is the answer? What's the answer? Yeah? 5. So it means that your B1 will be 5. Right? Then B2. B2. B2, what is it going to be? It's going to be 0. Yeah, it's going to be 0 because you cannot calculate it. You get what I'm saying? I want us to look at why I'm saying you cannot calculate it. Looking at this power, this is S raised to power 3, which means whatever is in the first column here is a coefficient of S raised to power 3. Is that clear? When we jump that, we go to S raised to power 1. Yeah? So it means that this is S raised to power 1. So it is present. When you come to the second one, we have S raised to power 2 here. Yeah? When we jump the next, we are going to have S raised to power 0, which is actually that. When we come to this, this is S raised to power 1. When we jump one coefficient, then what are we going to have? S raised to power negative 1. Do we have such in this equation? Yeah? So that is why it does not exist. Same with this, you will only get this. This one will obviously be 0 because this is the coefficient of S raised to power 0. So it means that after getting S raised to power 0, then the next one is we jump S raised to power negative 1. Then we go to S raised to power negative 2, which is not part of this equation. Is that clear? For this, it usually goes up to S raised to power 0. It does not go to the negative signs. Is that clear? So anytime you find this a coefficient that will lead you to the other one, to S raised to power a negative, then it means that that particular coefficient will not be existing. Is that clear? So that is how you will know that. So what is B2? B2 is 0. You say that. What of D1? D1? D1 is 12. So you don't need to calculate D1. S raised to power 0 will always be that. But if you want to calculate, you can still calculate. There is no problem. It's going to be 12 times 5, which is 60, minus 0 times 4, which is over 5, which is simply 12. And it happens for all the Routh array. The last coefficient will always be S0, will always be the constant there. So, is the system stable? So you are supposed to put a comment after that. Is the system stable? We say that you are supposed to look at the first column. All of them must be positive. Are they all positive? If they are all positive, then you can put a conclusion that the system is stable since all the roots in the first column are positive. The system is stable because all the roots in the first column are positive. The system is stable since all the roots in the first column are positive. So that is how you are supposed to deal with the stability. We can look at a second example. This determine. This example 2, sindio? Determine whether the system represented by the transfer function. So remember this one, you are given the transfer function, but the transfer function below is stable. And if not, determine the number of poles, determine the number of poles in the right half plane, in the right half plane. I think the pen, let me use another one. The right half plane, then we have 3s raised to power 3 minus 12s squared plus 17s minus 20 all over s raised to power 5 plus 2s raised to power 4 plus 14s cubed plus 88s squared plus 200s plus 800. So that is what we have for this. That is what we have. So that is the question. So we are supposed to determine whether this system is stable or not. So from the preliminary check, can the system be stable? Eh? It is stable. Yes. Kuna mwenye amesema no. Where is he? Atuambie why it may not be stable. Remember we said that you are supposed to use the characteristic equation. Huh? And when you are talking about the characteristic equation, we are using what is here. Not this. Huh? At the end, it may not be stable because we can see for these negatives to be there, then it means that there may be negatives down. Huh? Maybe that is why there is a question where you are being asked that. Huh? But from the preliminary check, using what we had discussed for the first step, the system is likely to be stable. Because looking at the characteristic equation, all the coefficients are present and positive. Is that okay? All the coefficients are present and positive, and therefore we can easily check. So it means that for us to confirm whether it is stable or not, then we must take it through the second step, which is now the Routh array. And then we develop the Routh array and do the calculation. So we can develop the Routh array in that manner. So we have s raised to power 5, s raised to power 4, s raised to power 3, s raised to power 2, s raised to power 1, and s raised to power 0. Then what is the coefficient for that? 1, unaruka hii, unaenda 14, unaruka hii, unaenda 200. Is that okay? Then we go to the next. Hapa 2, unaruka 14, unaenda 8 hapo 800. Then I can do the calculation for that, then you calculate the rest. Huh? I've done that one. Huh? Now you can go ahead and do the rest. So you can start with this. Huh? Maybe you can call it B1, B2, B1, B2. Looking at that, looking at this, huh? You don't need even to disturb yourself, because if this one is s raised to power 3, it means that that is power 3, that is power 1, that one is non-existent, right? Is that okay? If this one is raised to power 2, it means that this is raised to power 2, this is raised to power 0, that is again does not exist. Huh? Is that clear? If you talk about this, it is only this one that is going to exist. Huh? The rest are not going to exist. Huh? Is it true? Because this is raised to power 1, so you can only calculate that. We don't have raised to power -1, huh? Because if we jump one coefficient, it will be going to -1. Huh? Yeah, so you can calculate that, B1. Now this one you can call it C1, C1, C2. Then this one you can call it D1. Huh? So we can get B1, B2, C1, C2, and D1. Haya? B1? Yeah? Yeah? 2 times 14 minus 88 times 1 all over 2. So what is that? Yeah? -30. So that is -30. Then B2 here. What is it going to be? What? 2 times 200 minus 800 times 1 all over 2, which is it? Is that okay? It's minus 400 that. Then next, this one, C1. Minus 30 times 88 minus 200 times 2. So this negative times 2, then all over minus 30. So what do we get? That's got a lot of minus, so you must be very careful. Huh? Hmm? 74.67. You can simply say 74.67. What of C2? C2 is hapa. C2 cannot be 0. 800. It should be 800. So C2. How did you get 800? I know it is 800. It is true. It is 800. Minus 30 times 800 minus 0 all over minus 30, yeah, it is 800. What of D1? $74.67 times minus 200 minus 30 times 800. Then all over 74.67, which is so you can have that. What did you get C2 to be? 800. Then here minus 121. No, is it? It is 121, not minus. 121, let's say 0.4. Then you have been asked. The question was, determine whether the system represented by the transfer function below is stable, and if not, determine the number of poles in the right half plane. So is the system stable? Looking at the first column, so how many roots lie on the right hand of the S-plane? 2 roots. So if you want to determine the number of roots that lie on the right half of the S-plane, then you are supposed to come to the first column, yeah? Then you determine the number of times the sign have changed. So in the first column. Are we together? You determine the number of times the sign have changed from positive to negative and negative to positive. That is what you are going to use in order to determine the number of poles or the number of roots that lie on the right hand side of the S-plane. So how many times has the sign changed here? Yeah? How many times? 2 times. 1 time. Okay. You can do it physically. Check. Here. Here. Then here there is the first change. Is that true? To negative. Yeah. Then again here. It goes back to positive. So that is the second change. Then it is now positive all along. So how many times has it changed? So there are 2 roots that lie on the right hand side of the S-plane. So you just count physically that way, right? Which means if I have maybe another negative down here, then the number of times will increase. Are we together? Because it will have another negative, increasing the 3rd time. Then again it comes positive. It becomes the 4th time. So you must look at them, because the arrangement of the positives and the negatives may not be that very easy for you to determine. So just look at each and every root and count the number of times it has changed. It seems as if you have a question there. Yeah. Right half plane. Right half plane, when we started, I did mention that this one is, there is a little bit of attachment with the poles and zeros. Right? There is a little bit of attachment with the poles and zeros. So what we are referring to with the right half plane, we are simply talking about the S-plane. Sawa, where we had E delta T sine this side. Are we together? And we say that when this one happens, then the system can never be stable, because at T tends to infinity, as T increases, then it means that it is becoming more stable. If there is oscillation, it will be becoming more oscillatory. Right? So that is where that one comes from. So there is a little bit of an attachment from what we did as far as the root, the stability method by use of poles and zeros is concerned. So we are still there. So this one is what is borrowed from looking at the stability in terms of poles in zeros. Huh?
So when you are calculating the unknowns,
Yes.
maybe we start by inserting the values like
The first.
representing like B1, B2,
Yeah.
and then you start calculating.
Yes.
You substitute in back after each. Or
Yeah, you can.
substitute at that point.
You should substitute back. You can even draw two of this, no problem. Yeah, whereby the other one has got the B1, B2, then the next one is now complete after the calculation. Huh? Are we together? Yes. Or you can have a space and do the calculations inside there and write the answers. Yes. You are supposed to. What is important is you show you are working. Are we together? You are supposed to show you are working. And then you remember that, like in this case, when you will be discussing that, you must be able to show the columns. Yeah, if the columns have got B1 here and B2, then somebody will see that maybe you have not completed. So you can draw the two. You can draw one with a known, calculate the unknowns, draw another one, fill. Is that okay? Are we together? Yes. Or you can draw one, have space, do your calculation inside here. Right? And then you will be giving your answers right inside the table. Are we together? Yes. But the most important thing is that whatever you have been doing is not hidden somewhere. Yeah, don't go with your calculations in your mind and waiting for the marks. Eh? Is that clear? Yes. So that is what we can do. I think we can look at, still there are several examples because I'm trying to explore how this can always be asked. So we are going to look at another example, yes? Oh, the statement you can say, the system is unstable and two roots. The system is unstable and two roots lie on the right half plane and two roots lie on the right half plane. The system is unstable and two roots lie on the right half plane. Yes, another. Write this down. I think it has some drawing, so maybe we can do that. The open loop transfer function. The open loop transfer function of the open loop transfer function. The open loop transfer function of a negative unity feedback. The open loop transfer function of a negative unity feedback. The open loop is given by the equation G of S. Is given by the equation G of S is equals to K all over S into S plus 4. Is given by the equation K is equals to S into S plus 4 into S plus 5. Into S plus 5. Find the range value of K. The range value of K for marginal stability. For marginal stability. So this is now the T transfer function, and it is given by a negative feedback. So remember, this is now the forward element. So the first thing, you're supposed to get the overall transfer function. Then from the overall transfer function, that is now where you are going to get the characteristic equation from. Then after obtaining the characteristic equation, you take that particular characteristic equation to the Routh array. So let's look at what is it that we are going to do. So the solution. So for you to do that, maybe with the first thing that we can do, we can draw this so that we have that in that manner. So that K all over S into S plus 4, S plus 5. That manner, so that you have that. Then from there, we can have this and we have been told that it is unity feedback and it is negative. Is that okay? Then that is now what we are going to have. So the first thing that we can say that this is now R of S, then that is the comparator, and this is now C of S. Then the next thing that we are supposed to do is to get the overall transfer function of this. So given this, you are supposed to get the overall transfer function first, so that you get the characteristic equation. And remember, in this case, there is a known, there is a K. So we have been asked to get the range value of K for marginal stability. So what we are going to do is to get C of S. C of S all over R of S will be given by G all over 1 that GH, which is simply going to be K all over S into S plus 4 into S plus 5. I believe you are able to differentiate between my S and 5 all over 1 plus K all over S into S plus 4, S plus 5. So that is what we are going to have. Then that one, you simplify it so that you're going to have K all over S into S plus 4, S plus 5 plus K. Is that okay? Then now you can expand to write it in form of a polynomial equation. You can expand that. So if we expand that, you are going to have is S squared plus 4S, you multiply by S plus 5. Sindio? Yeah? So maybe S squared plus 4S, you multiply by S plus 5, so that you have S cubed plus 4S squared plus 5S squared plus 10S, then plus K. So this is going to be S cubed plus 9S squared plus 10S plus K. I think that is what it's supposed to be. So it is S cubed. So this is going to be K all over S cubed, if you expand it, plus 9S squared plus 10S plus K. So that is what we are going to have in that case. Then now you have your characteristic equation. So this is what you take to the Routh array and do your calculations. But remember, you have the value of K here, which means there is a known. So in that case, we take it to the Routh array, S raised to power 3, S raised to power 2, S raised to power 1, and S raised to power 0. So we can have that in that case. So which one, what do we write here? Eh? Then hakuna kitu ingine, si ndio? Then the next one? Then we calculate that. I think it is only one that we are supposed to calculate. So 90 minus K over 9. So we are saying 90 minus K all over 9. So we can write it here. Or somebody can still say 10 minus, is it K over 9? 90 minus K all over 9. There was a problem in expansion. This is supposed to be 20. Sindio? Yeah? There was a problem in expansion. Therefore, it means that this is supposed to be 20. So there is a likelihood that I'm alone. I've just realized that I was lonely without my knowledge. Yeah? 180 180 minus k over 9. Huh? So here we are going to have 180 minus k all over 9. Huh? 180 minus k all over 9. 180 minus k all over 9. So from there, we are supposed, what was the question? Find the range value of k for the marginal stability. So we are going to look at the k is unknown, huh? Right? The k is unknown. So if the k is unknown, then what it means is that wherever there is k, we can see that, we look at the first column, 1 is positive, so we don't have a problem with that. 9 is positive, we don't have a problem with that. Is that true? So we have 180 minus k all over 9 must be greater than 0, because when it is greater than 0, that is when it is positive. Are we together? Yeah, from what we talked about as far as the Routh stability method is concerned, all the values in the first column must be positive. Huh? So for that one to be positive, then it means that this one has to be greater than 0. Then the other equation, we have k, so it means that k should also be greater than 0. Then you can solve that inequality. Then get the answer for the range value of k. So k should be greater than 0, but it should be less than. What is it that it should be less than? Huh? So this one will give you the value that k should be less than. Huh? This one should give you the value that k should be greater than. So with that, you shall have determined the range value of k. So k should be between this and this. Huh? So k should be greater than 0. Yes. And less than 180. Less than 180. This way. Hivyo. Eh? So you want us to say k should be greater than 180. It doesn't matter. What matters is the directions of this. Like now, do you all agree? Eh? Because what we've done here, you can just solve it normally. 180 minus k all over 9 is equals to 0. Then cross multiply 180 minus k is equals to 0. Are we together? Then it means that k is equals to 180. So that is where we are getting that. Yeah? Is that correct? So that one is the range value of k. Then that one you have concluded. Think we can do the same for another one. But this one now, you are going to do the first part or the second part. You say, in the figure below, find the value of k for marginal stability. 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 And also determine the natural frequency of oscillation. And also determine the natural frequency of oscillation. And also determine the natural frequency of oscillation. So the figure is here. The figure is on the board. And also determine the natural frequency of oscillation. So we can do that. Consider, when you are not always told, then consider negative feedback. Are we together? So that you don't have positive, negative value on the transfer function. So you always consider a negative feedback in case it is silent. Because actually what you will realize when you talk of the positive feedback, it always generates oscillations. And therefore, in most of the control systems, there is always negative feedback to enhance stability of a system. Huh? Yes. So that is what it is. You are supposed to look at that. Then you are supposed to get the range value of K, and then we are going to see how we can get the frequency of oscillation, the natural frequency of oscillation, the omega n. So we have C of S all over R of S is going to be G all over 1 GH, is it? Then that is now going to give us K all over S into S squared plus S plus 2 all over 1 plus K all over S into S squared plus S plus 2. So that is what we have. So that one, if it is simplified, we are going to have K all over S cubed plus S squared plus 2S plus K. Yeah? And that is what we take to the Routh array. S raised to power 0, S raised to power 3, S raised to power 2, S raised to power 1, and S raised to power 0. Then here is 1, 2. Here is 1 K, K. Then 2 minus K over 1, which is simply 2 minus K. Yeah? Then from there, we can now find the value of, so for that one, for marginal stability, 2 minus K has to be greater than 0, and K also has to be greater than 0. So therefore, how do we write that? I was told that I'm supposed to write it as K is greater than 0. But less than 2. So that is the values. Those are the values, the range value of K. And now we can go ahead and look at what we call the oscillation frequency. So what do we do about the oscillation frequency? So for the oscillation frequency, always you are supposed to come to the S squared term all the time. Sawa sawa. Then rewrite that equation, and then you take the highest value of K. Is that okay? Is that okay? So this one looks like fun. It is funny. It's supposed to be K. Sawa sawa. So if we write that equation and take the highest value of K, the highest value of K is 2. Then here we have, if we write the whole of this equation, it is going to be S squared, sindio? Are we together? Plus 2. Yeah? And then we are supposed to compare it with the equation S squared plus omega n squared. Is that okay? We are supposed to compare it with that equation. Then after comparing it with that equation, then we are supposed to, you must ensure that the coefficient of S squared are the same. Yeah? Is that okay? Then if the coefficients are the same, like if this one was even 10, then you have to divide everything by 10 so that that one is at unity, this one is at unity. Then if that is unity and this is unity, then it means that this and this should be equal. Huh? Sawa sawa. So then you simply say omega n squared is equals to 2. Therefore, omega n is equals to root of 2, which is 1.414 rads per second. So that is how you obtain the frequency. Yes?
So you're supposed to go back to the dimensionless equation?
Not dimensionless equation. This equation is always referred to as, it is not necessarily dimensionless equation, but it is a simple harmonic equation that is supposed to be used. And you are supposed to have that. I'm looking at where I wrote something about it so that we can make reference to that. Or the other thing that somebody can also do is you go to this equation, then find its root, get the roots of that particular equation. That is another way that you can use that in order to determine that. Then from there you will be able to get that. So it is called a simple harmonic equation. Simple harmonic equation, s squared plus omega n squared. So always when you are asked that, go to the second, to the power of 2 in any equation. Sawa sawa. After filling the Routh array, go to the power of 2. Then after going to the power of 2, you are supposed to take the highest value of k. Yeah? Even if we say that it is maybe k plus some value, let's say 100, then I will say k is 2. Then I will say that is now going to be 102. Is that okay? What you need to do for you to get the frequency, you just come to the s raised to power 2, then you compare with that particular equation. Sawa sawa. And then get that. I think that one is what you are supposed to get. I want you to try this. Yes?
What is a scenario where you have the squared and the 2?
Yeah?
That is the equation you've given us.
Yes.
We're going to use it now.
So the equation that is general is this. So this one is from here.
What if it could have been s squared plus 4s plus 2?
It can't be 4 squared plus 4s plus 2 because when you go to the s squared, the only term that can be there is term for the 0 power. It cannot be another power. Sawa sawa. Are we together? This term, it means that this is s raised to power 0. Is that clear? So it cannot be another s squared plus something plus 2 unless the value of k here, the value that you get here is k plus something, of which you are still going to get the highest value of k and add to whatever value that was there before. Are we together? Yes. I think we can try this. I'm going to give you this one. You can try. And then from there, I think this one, you do it until you get to the Routh array. Write down this. The open loop transfer function. The open loop transfer function. The open loop transfer function of a unity feedback control system. Of a unity feedback control system. Of a unity feedback control system is given by g of s is equals to k all over s plus 2 s plus 4 s squared plus 6s plus 25. Plus 25. Find the range value of k for marginal stability. Find the range value of k for marginal stability, and also determine the natural frequency of oscillation. Find the range value of k for marginal stability, and also determine the natural frequency of oscillation, and also determine the natural frequency of oscillation, and also determine the natural frequency of oscillation. So I want you to do that one. And I want to see how you are going to enter your Routh array first before you can get to all those other values. I think we can start. And 200 is s raised to power. So they are both the same. Because here we are dealing with powers. Yeah? Yeah. So when you form the Routh array, what are you going to have? S raised to power 4 from this equation. What do we have? S raised to power 4, S raised to power 3, S raised to power 2, S raised to power 1, and S raised to power 0. So hapa. Then 69, 200 plus k. Then here, yeah, 12. 198, 0. Then here is And have you done all the calculations? Eh? 52.5 here. 200 plus K. This one does not exist here. 79.95 minus 12K all over 52.5. Then here, that is 0. That cannot be 200 plus K. Hii. Oh, hii ya chini already tumeandika. This one you don't need to calculate. This one you just bring it directly. Eh? You don't need to stress yourself by calculating that. Eh? So, after that, the range value of K, first column, 200 plus K should be greater than 0. And 79.95 minus 12K over 52.5 should also be greater than 0. So that is what you are supposed to get. So what you get from there, K should be less than what and greater than what? K is greater than 200 but less than 666.25. So that is the value. Then after that, we are supposed to get the oscillation frequency, which is now going to be, so you come to this. For the oscillation frequency, you still come to that. Not that, it is up to here. Is it? Which is now going to be 52.5 S squared plus 200, we can say 866.25. Should be equivalent to S squared plus omega n squared. So that is what you are supposed to get. So before you compare, you must ensure that everything is divided by 52.5. So that this one is S squared, that is S squared. And if this is S squared and that is S squared, it means that that and that will now be the same. So we are going to have 52.5 should be S squared plus omega n squared. Is it? Yes. The highest value of K is 666.25. Yes, plus 200. That is where 866. So this is plus 200. This one plus 200. So we have taken this 200 plus K. What is the highest value of K? 666.25. So it is becoming 866.25. Then that is now what you have. So what is your answer? .06 rads per second. So what remains is there is a very small bit for the special cases. That is what we are going to look at. We will spend a few minutes of our next meeting so that we look at the special cases of Routh array before we get to the graphical methods, because this one is actually going to be the end of analytical methods of stability. Is that okay? So that I think next time you should come with Nyquist plot. Polar plot. Yeah? I'm going to see if I can get one so that you can make a copy and have it. How many do we have? I think I can start with the graph paper first. Yeah?